Welcome to the deep dive. Today we're digging into something absolutely foundational, literally. We're talking about the relationship between buildings and the ground they sit on. A relationship that's often invisible, but becomes critically important when, the earth starts moving, like during an earthquake. Think of it as the earth and our structures having this vital, dynamic conversation.
And that conversation has a name, soil structure interaction, or SSI.
Yeah.
It's a field that really gained traction back in the 1960s and 70s,
Yeah.
precisely because engineers started realizing the ground isn't just, well, a passive block supporting a building.
Exactly. And for this deep dive, we've pulled from some fantastic sources you shared. There's a really detailed FEMA guide, academic lectures, research papers, quite a bit.
Yeah, some good material there.
Our mission is to take all this complex information and, unpack this crucial dance. We want to highlight the key players, the surprising ways they influence each other, and give you those aha moments about why understanding SSI is so vital, and hopefully do it without getting lost in, dense engineering textbooks.
Right. Because the simplest way to think about a building, it's often imagining it bolted rigidly to, unmoving bedrock. But the real world is far more dynamic. The soil beneath isn't just a static base. It actively influences how a structure responds to forces. And here's the really interesting part. The structure influences the soil right back.
So it's very much a two-way street then.
Absolutely.
The soil's flexibility can dramatically change the forces a building feels, and the building's swaying can actually send waves back into the ground.
Yeah, creating new vibrations.
This is a huge departure from those simpler models that just assume a fixed, rigid base.
Precisely. And while those simpler assumptions work sometimes, they can completely miss critical behaviors, especially with softer soils or significant ground shaking. We're dealing with a coupled system where the building itself, the superstructure,
Right?
its connection to the ground, the foundation,
Okay.
and the soil beneath, with all its complex properties, are constantly interacting, constantly influencing each other's response.
So the core question we're exploring today is, when does this give and take, this dynamic relationship between the ground and the building, really become essential to understand? When can't engineers just assume that solid, unmoving foundation?
Well, at its heart, SSI is that dynamic, interdependent relationship. It's where the building and the soil beneath it mutually influence each other's behavior, especially during events like earthquakes. It's not just the ground shaking the building. The building's reaction creates forces and waves that go back into the ground,
Okay.
which in turn affects the building again. It's a feedback loop.
Okay, so mutual influence and feedback are key. And as you said, the system involves those three main parts. The superstructure, that's the building you see.
Correct.
The foundation, that's the part connecting the building to the earth.
Right, the interface.
And the soil itself with all its unique properties.
That's it. And they're in constant communication through a few main mechanisms. First, there's stress transferred. The building pushes down and sideways on the foundation, stressing the soil, and the soil pushes back. Pretty straightforward.
Force is going back and forth. Got it.
But then there's motion modification. This is where it gets fascinating. The presence of a large, stiff structure and its foundation can actually change how seismic waves travel near it.
Really? How?
You can filter some waves out or even redirect them. And ultimately, the way the whole system, soil, foundation, and structure vibrates is a result of how all these unique parts are interacting together.
The sources you provided use some specific language to talk about this. Let's get clear on a few key terms. What do engineers mean by free field motion or FFM?
FF is essentially the baseline ground shaking. It's the motion the ground would experience at a particular spot if there were no building there.
Ah, okay. The raw input.
Exactly. It's the raw, undisturbed seismic wave motion. Engineers figure this out through analyzing local geology or using standardized code-based ground motion predictions. It's the starting point.
So the ground shaking in its natural state. Now, how does the foundation change that FFM? That brings us to kinematic interaction, right?
Exactly. Kinematic interaction is all about how the presence of that rigid foundation changes the FFM before the building even really starts swaying much. A large, stiff foundation. It can't follow every tiny ripple of the ground motion like loose soil can.
Right, it's too stiff.
It tends to average out the motion across its base, especially filtering out the higher frequency wiggles. Think of a big, stiff raft on choppy water. It sort of smooths out the small, fast waves.
Okay.
This includes things like seismic waves scattering off the foundation, or how shaking changes with depth for buried foundations, the embedment effect.
Okay, so the foundation itself acts like a filter on the incoming ground motion. That makes sense. What happens once the building starts swaying? That's inertial interaction.
Yes, that's where inertial interaction kicks in. Once the building gets motion from the what we call the foundation input motion, or FAM, it starts to sway.
Yeah.
The building's mass resists this movement, creating inertial forces, like pushing back against the sway. These forces get transmitted down into the foundation and back into the soil.
Ah, okay. Back down.
This pushes and pulls on the soil, causing it to deform and radiate seismic waves away from the building. That radiating energy acts as a form of damping, soaking up some of the vibration. We call it radiation damping.
Radiation damping.
It's
like
a constant back and forth. The building moves, puts forces on the soil deforms, which affects the building's next movement.
That's a great way to put it. Kinematic is the ground motion affecting the foundation before significant building sway.
Right.
And inertial is the building sway affecting the ground after it starts moving.
Exactly.
And FM, then, is the motion the base actually feels after that initial filtering from kinematic interaction.
Precisely. FM is the modified ground motion at the base of the structure, the motion the building's inertia then responds to.
Okay, switching gears a bit, soil liquefaction sounds pretty terrifying.
It absolutely is. It's one of the most devastating soil failures. In saturated, loose, granular soils, think sandy or silty soils below the water table during strong shaking. The water pressure between the soil particles can build up so much that the particles lose contact with each other.
Is contact.
Yeah, the soil temporarily loses almost all its strength and stiffness and behaves like a heavy liquid.
Like a liquid, wow.
Yeah. Foundations can sink, tilt dramatically, or buildings can even collapse because their support essentially vanishes.
Pure nightmare fuel for anyone who designs or lives in buildings.
Okay.
What's the system natural period?
That's the time it takes for the entire soil foundation structure system to complete one full cycle of vibration if it were disturbed and allowed to sway freely.
The whole system together.
Right. On a fixed, rigid base, you just have the building's natural period.
Oh.
But when you add the flexibility of the soil,
Yeah.
it generally makes the whole system sway slower.
Slower.
Think of hanging a weight on a flexible rubber band versus a stiff wire. The rubber band lets it bounce much slower. Soil flexibility is like adding a flexible spring at the bottom.
So the building soil system sways slower than the building alone would on rock. Okay. And soil stiffness, often measured by its shear modulus G.
Soil stiffness G is a measure of how much the soil resists shearing or twisting deformation. It's absolutely critical for SSI because it determines how much the soil will deform under the building's forces. But here's a really key insight. Unlike steel or concrete, soil stiffness isn't constant.
It's not.
No, it's highly strain dependent.
Strain dependent.
Meaning, the more the soil is pushed, pulled, or shaken, the higher the strain, the softer it gets. Its stiffness decreases.
Ah, okay.
This nonlinear behavior is a major factor in SSI analysis and makes accurate predictions challenging.
So the soil changes how stiff it is depending on how hard you push it, adds another layer of complexity. What about damping?
Damping is simply the dissipation or loss of energy within the system during vibration. The overall system damping includes damping within the structure itself, but also from the soil foundation interaction.
Okay.
Soil has internal friction. We call it material or hysteretic damping, where energy is lost as particles rub against each other. And then there's radiation damping, which we mentioned with inertial interaction, energy radiating away from the foundation as seismic waves.
Like ripples in a pond.
Exactly, like ripples spreading out from a stone dropped in a pond. More damping means vibrations die out faster, which is generally a good thing.
Got it. Energy loss. Finally, the sources mention different ways engineers analyze SSI, direct and substructure methods.
Right. These are the two main modeling philosophies. The direct method is the everything-in-one approach. You model the soil, the foundation, and the structure all together as a single system in one big computer model, often using methods like finite element analysis, FEA.
The whole thing at once.
Yeah. The big advantage is it captures the full complexity, nonlinear soil behavior, complex foundation shapes, how waves travel through the soil. The downside, it's computationally intensive, requires vast amounts of really detailed soil data, which can be hard and expensive to get.
Demanding.
Very. It's powerful but demanding.
Modeling the whole shebang at once. How about the substructure method? That seems to be mentioned more in practical design guides like FEMA P20s and 91.
That's the more common approach for routine design, precisely because it simplifies things by breaking them down. It's a step-by-step process. First, you analyze the kinematic interactions separately to figure out the actual motion hitting the base.
Step 1, get the thumb.
Step 2, you characterize the soil-foundation interaction using what are called impedance functions.
Impedance functions.
These are essentially mathematical ways to describe the soil's dynamic stiffness and damping resistance at the foundation level across different vibration frequencies.
So they sound like the soil's dynamic springs and dashpots.
Exactly. You can think of them that way. They represent how springy and how squishy the soil is, dynamically resisting foundation movement. The third step is you take those impedance functions and incorporate them into your structural model, often representing the soil's effect as frequency-dependent springs and dashpots at the base of the structure.
Ah, okay.
Then you analyze the structure's response to the FEM with this flexible base support.
That makes it easier to picture.
It's much more computationally efficient and practical for typical building designs, though it might not capture the absolute finest nuances of the coupled system compared to the direct method.
Okay, so now we have the language. Why does all this matter? Why can't engineers just assume a fixed base and be done with it? Let's start with the most obvious reason. Earthquakes.
During an earthquake, ignoring SSI means missing fundamental changes in how a building behaves. First, there's that period lengthening we talked about. The building sways slower.
Yeah.
This can be a benefit if that slower sway moves the building's vibration period away from the dominant, most energetic frequencies of the earthquake ground motion at that site.
So lower forces?
Potentially, yes.
Right.
Lower forces. But, and this is a massive but, if that lengthened period happens to match a period where the ground itself is naturally amplifying shaking, like on deep, soft soils, you get resonance.
Resonance. That sounds bad.
And resonance is a disaster scenario. It dramatically amplifies forces and displacements.
Ah, the double-edged sword. Slower sway can be good, but matching the ground's rhythm is terrible.
Precisely. SSI also adds damping that energy dissipation from soil friction and radiation.
Right, the shock absorbers.
Exactly. More damping means less intense vibrations and potentially less damage. So SSI introduces flexibility and damping into the system.
And it impacts the foundation itself, not just the building above.
Absolutely critical. SSI analysis provides a much more realistic picture of forces and deformations acting on the foundation, including things like bearing capacity under dynamic loads, the potential for uneven settlement or tilting, or even sliding and overturning risks during extreme shaking.
Things a fixed-base assumption wouldn't show.
Exactly. A fixed-base assumption gives you none of that.
Which sounds like it could lead to serious safety failures if not considered.
It can. Getting SSI right is fundamental to designing foundations and structures that can safely withstand seismic events. And history is unfortunately full of tragic lessons where SSI played a starring role.
Like Mexico City.
Mexico City in 1985 is a classic, heartbreaking example. The city sits on very deep, incredibly soft, former lake bed clays. This soil has a very strong natural period of vibration, around 1 to 2 seconds.
Okay.
The earthquake shaking coming from bedrock actually got massively amplified by this soft soil layer. Many mid-rise buildings, say 10-20 stories, on these soft soils had their natural periods lengthened by SSI into that exact same 1-2 second range.
Oh, no.
The result was catastrophic resonance. The soil and the buildings were vibrating in sync, leading to widespread, devastating collapses. Buildings that might have survived on stiffer ground. It's a stark, real-world demonstration of SSI's negative potential and how site-specific it is.
Just devastating.
Then there was Kobe in 1995, which brought widespread attention to soil liquefaction and how it completely undermined foundations due to SSI effects. And more recently, Christchurch in 2011, where liquefaction caused immense damage across the entire city, sinking and tilting buildings everywhere.
These aren't abstract ideas. They're real disasters that show just how critical SSI is. But it's not only about earthquakes, is it?
You're right, that's a great point. It pops up in many other places, too. For very heavy structures on soft, squishy soils, understanding SSI is crucial for predicting how much the building will settle over time, and whether that settlement will be even or cause structural problems.
Settlement, right?
For industrial buildings with heavy vibrating machinery, SSI analysis is needed to make sure those vibrations don't cause problems for the structure or sensitive equipment, or get transmitted to nearby buildings.
Makes sense.
Even tall, slender structures under wind loads. Their dynamic sway and stability are influenced by how much their foundation rotates or shifts due to interaction with the soil. It's also key for offshore structures on the seabed, or analyzing how new tunnels or excavations might impact existing buildings nearby. It's a fundamental part of structural behavior whenever dynamic loads are involved, not just seismic.
Let's cycle back to kinematic and inertial interaction for a moment, because I think understanding the difference is one of those key insights. We established FFM is the raw shaking. How does kinematic interaction really change that baseline input?
Okay, kinematic interaction. It's purely due to the foundation's physical presence and stiffness within the soil mass before the building starts swaying significantly. It modifies the FFM through several mechanisms. First, wave-scattering seismic waves hit the foundation and bounce off or bend around it. Second, base slab averaging that large, stiff foundation base averages out the complex ground motion across its width, essentially filtering out the high-frequency, short-wavelength components.
Smoothing it out.
Exactly.
Yeah.
Third, embedment effects, if the foundation is buried. The soil surrounding the basement walls constrains its movement, and the motion itself varies with depth. The result of all this is the FIM, the motion the building base actually receives, which can be quite different from the FFM measured nearby.
So the foundation filters the ground's natural movement before it reaches the building. Then the building starts swaying, and that's inertial interaction. How does that feedback loop really work in practice?
Right. Once a building is receiving that FIM and begins to sway, its inertia creates forces at the foundation level. These forces act on the soil, causing it to deform further than it would have under just the FFM or MO alone.
Okay, the building adds force.
Yes. And this deformation is what generates those outgoing seismic waves, leading to radiation-damping energy escaping the system. It's like the building is using the soil as a medium to shed energy.
Shedding energy, I like that.
This inertial interaction fundamentally alters the natural vibration characteristics of the whole system. It changes its period, makes it longer, and adds damping. So the building's movement influences the soil, and the soil's response influences the building's next movement. It's a continuous, dynamic partnership.
That really clarifies the two-way street concept. Given all this complexity, when does an engineer have to do a detailed SSI analysis? Are there specific types of structures or soil conditions that are, red flags?
Yes, absolutely. There are key scenarios where ignoring SSI would be irresponsible. The most significant is heavy, relatively stiff structures built on soft, compressible soils.
Heavy and stiff on soft.
Think a multi-story concrete building on deep clay or loose sand. SSI effects are typically maximized here. You get substantial period lengthening and potentially significant amplification or reduction of forces depending on the earthquake's characteristics.
Okay, heavy and stiff on soft is the big one.
Right. On the flip side, light, flexible structures on very stiff ground, like rock, usually experience minimal SSI. A fixed base assumption is often perfectly adequate there.
Light and flexible on rock, probably okay.
Probably. However, for critical infrastructure hospitals, emergency centers, major bridges, nuclear power plants, even very tall buildings, a detailed SSI analysis is almost always mandated regardless of soil conditions.
Why is that?
Simply because the performance requirements for safety and continued function are so high, you can't afford to get it wrong.
Makes sense. You can't take chances with those.
And industrial facilities, housing sensitive equipment or hazardous materials, often require careful SSI analysis just to ensure vibrations are controlled and there are no stability issues. So while heavy on soft is the prime case, critical structures on any soil generally need it.
Is there a way to quickly gauge if inertial SSI might be important for a particular building? A simple check.
Yes, there's a helpful screening parameter engineers use. It's a ratio comparing the structure's flexibility and size to the soil's flexibility over the depth influencing the interaction. Roughly, you're looking at the structure's period and height relative to the soil's shear wave velocity and the foundation's width.
Okay, a ratio.
If this ratio is greater than about 0.1, it's a strong indicator that inertial SSI effects are likely significant enough to warrant a more detailed look.
So a quick check, if it's over 0.1, dig deeper.
Exactly. It's a quick filter to know whether you can likely ignore SSI or if you need to investigate further. And importantly, you need to use a relevant soil velocity for that interaction depth, not necessarily just the standard VS30.
Okay, so there are ways to know when to spend the effort on a detailed analysis. What are the key parameters engineers need to nail down for that analysis? What kind of data is critical?
Well, at the top of a list is accurate soil data. You need to understand the soil's dynamic properties, especially its stiffness, the shear modulus G, and its damping ratio. And crucially, how these properties change with strain level, that nonlinear behavior we mentioned.
A strain dependency, right?
Yeah, absolutely. You also need detailed information about the foundation.
Yeah.
Its type, is it a shallow mat, spread footings, deep piles, its size, its shape, and how deeply it's embedded.
Foundation details are key.
Then you need the structure's dynamic properties. Its mass distribution, its stiffness, its inherent damping. All of these factors influence the overall system period and how energy is dissipated.
And how do different soil types and foundation details change the picture?
Oh, it's night and day. Soft, plastic clays, low stiffness, relatively high damping lead to huge SSI effects, especially significant period lengthening. Loose, saturated sands have moderate stiffness but carry that major risk of liquefaction, huge settlement potential, and highly nonlinear, complex behavior.
Liquefaction again.
Yeah. Denser gravels and sands are stiffer and drain better, generally leading to less dramatic SSI and better performance. And then you have bedrock, very high stiffness, low damping, where SSI is usually minimal. But the structure's response might be dominated by higher frequency shaking then.
So very different responses.
And the actual layering of different soil types creates complex wave interactions. Foundation embedment depth dramatically changes how motion is transmitted. Well, the sheer variability of soil is one of the biggest challenges.
Let's talk more about modeling, because this is where those concepts turn into practical engineering work. We touched on the direct and substructure methods. Can we walk through how an engineer actually uses these? I think visualizing how they tackle this complexity could be a real eye-opener for listeners.
Absolutely. Let's start with the direct method again. Imagine building a single, massive 3D computer model. It includes a large volume of soil surrounding and beneath the foundation, plus the foundation itself, and the entire structure above. You divide this whole system into thousands, maybe millions, of tiny elements. That's the finite element, or finite difference part.
Okay, tiny pieces.
Then you apply the seismic shaking to the base of the soil model, or maybe its edges, and solve complex mathematical equations for how every single one of those tiny elements moves and interacts over time.
Like simulating the earthquake moving through the ground and into the building all at once.
Exactly. It's comprehensive.
Yeah.
It excels at capturing things like nonlinear soil behavior under intense shaking, complex foundation shapes, or how seismic waves reflect and refract. You can see detailed stresses and deformations everywhere.
Sounds powerful.
It is. But, as we said, it's computationally expensive, can take days or weeks to run, and requires really detailed soil property mapping, often used for very complex or highly critical structures.
Okay, so direct is powerful but demanding. How does substructure simplify this for everyday design?
Substructure breaks it into manageable pieces. From step 1, figure out the kinematic interaction.
Get the thumb.
Right. You might do a separate, smaller analysis just of the foundation embedded in the soil to see how the free field motion gets modified into the foundation input motion due to base slab averaging and embedment. Step 2, figure out the soil foundation properties. This is where you calculate those impedance functions we talked about.
The dynamic springs and dashpots?
Essentially, yes.
Yeah.
You might conceptually push and pull the foundation in the computer model and see how the soil resists it dynamically across different frequencies.
So you're essentially creating a dynamic signature for the soil's resistance at the foundation level.
Precisely. You're characterizing the soil's springiness and squishiness dynamically. Step 3 is where you bring it back to the structural analysis. You take your structural model of the building itself, but instead of fixing its base, you attach those calculated impedance functions, those frequency-dependent springs and dashpots at the base.
Plug them into the structure model.
Right. Then you apply the FAM from step 1 as the input motion to this flexibly supported structural model and analyze its response.
Attaching dynamic springs and dashpots at the base makes the soil's effect much more intuitive to visualize. It sounds like this is much more practical for design offices.
Much more. It's far less computationally intensive. You can use standard structural analysis software for the final step, and the geotechnical part is simplified into these impedance functions. FEMA P2091 provides detailed procedures for this method, making it accessible for routine design projects, even if it involves certain simplifications compared to the direct method.
One of the sources, I think a lecture you included, mentioned needing special elements to model the contact surface between the soil and the foundation. Why is that interface so important?
Yes, that interface is absolutely crucial. Soil and concrete or steel foundations have vastly different stiffness.
Right, very different materials.
When shaking happens, they don't always deform perfectly together. You can get complex behavior right at that boundary. Maybe the foundation lifts slightly off the soil that's tension cracking or gapping, or it slides sideways, or zones of intense shear strain develop just beneath the foundation edge.
So slipping and sliding.
Exactly. Special contact elements in sophisticated models like the Goodman element you mentioned are designed to simulate this nonlinear behavior at the joint. Getting that contact model right is vital for accurate force transfer and predicting behaviors like uplift or sliding.
So, in a real SSI analysis, beyond picking the method, what specific factors do engineers really have to scrutinize? The difference between FFM and FEFM seems like one of them.
Absolutely critical. Recognizing that the FEFM reaching the building base is not the free field motion is fundamental. Engineers must carefully account for kinematic effects, like base slab averaging how much that big foundation smooths out the high frequencies. Codes often provide simplified ways to estimate this reduction based on foundation size, though with limits.
Okay, base averaging.
They also need to consider embedment effects, how burying the foundation deeper generally reduces the amplitude of motion and influences rocking. Again, codes provide modification factors, but these need careful application, often based on factors like the percentage of the foundation area in contact with the soil below ground level.
Embedment, too.
And then, yes, incorporating the inertial feedback that modifies period and damping is the other side of the coin. Getting both kinematic and inertial effects right is key.
And buildings with basements, they're not just sitting on the ground surface, they're embedded. Does that add a different layer of SSI?
It absolutely does. Basements mean the foundation walls are in contact with soil laterally, not just vertically beneath the base.
Right, the sides matter, too.
Exactly. This lateral interaction provides significant resistance to swaying and rocking notions. You can't just treat the base at the bottom of the basement as if it's sitting in open air. Properly modeling the lateral stiffness and damping provided by the soil interaction with the basement walls is vital.
How do they do that?
Concepts like the bathtub model, treating the rigid basement as interacting with the surrounding soil through horizontal springs, are simplified ways to think about it. ASCE 716 has some limited guidance, but modeling this correctly is key, often focusing the base of the system at the lowest level of the basement.
Okay, balancing kinematic filtering, inertial feedback, embedment, basements. It's complex. What's your key advice for engineers trying to get reliable SSI results? What are the must-dos?
Okay, several critical points. First, know when SSI matters. Use those screening rules of thumb to determine if a detailed analysis is warranted. Don't just do it because you can, and certainly don't ignore it when it's critical.
Step 1, is it important here?
Step 2, invest in good site characterization. SSI analysis is only as reliable as the soil data you put into it. Geotechnical investigations need to provide dynamic soil properties relevant to the expected strain levels.
Garbage in, garbage out with the soil data.
Exactly. Third, choose the right modeling approach. Direct or substructure for the specific project's complexity, criticality, and your team's expertise. Develop realistic, validated models, paying special attention to the soil, the foundation, and that crucial interface between them.
Pick the right tool.
Fourth, define the seismic input accurately. Ideally, this means a site-specific seismic hazard analysis considering local geology and different wave types. Understand where your input motion is applied in the model at bedrock, at the surface, as this significantly changes results. We saw examples from Wenchuan on that.
Get the earthquake right.
Fifth, account for soil nonlinearity, especially for strong shaking. While often simplified in practical design, understanding how soil stiffness decreases with strain is vital. Sixth, perform sensitivity studies. Soil properties have inherent uncertainty. See how varying key soil parameters like stiffness within a reasonable range impacts your results. Codes like ACE7 often require checking plus or minus 50% stiffness values for conceptual springs to understand sensitivity.
Check the what-ifs.
Precisely. Seventh, and perhaps most important, apply sound engineering judgment. These analysis tools are powerful, but they are aids to thinking, not replacements for it.
Trust your gut, too.
Well, your informed gut. Eighth, foster collaboration. Structural and geotechnical engineers must work closely together on SSI projects. Neither discipline can do it effectively alone.
Teamwork.
Absolutely. Finally, document everything meticulously. All assumptions, input data, modeling choices, results, and interpretations. The field is constantly evolving with updated codes and guidance documents like FEMA P2091.
Let's circle back and recap those core SSI phenomena, really zeroing in on their practical impact during an earthquake. Period lengthening. How does that practically change the building's experience?
Okay, period lengthening means the building will sway slower than it would on rigid ground. This shift can push its natural vibration period away from the peak energy periods of the earthquake motion.
Which can be good.
Which can potentially reduce the forces the structure feels. It's like shifting gears to ride the bumps more smoothly. But, as we saw in Mexico City, if that lengthened period aligns with the soil's natural amplification period, you hit resonance and forces skyrocket.
Bad resonance.
Very bad. It's the difference between avoiding the biggest punch and taking it head-on, amplified.
And foundation damping that energy loss. How does that practically help?
Foundation damping from soil friction and those waves radiating away increases the overall energy dissipation of the system. It's almost always a good thing. It acts like a shock absorber or a brake, reducing the amplitude of vibration.
So lower forces.
Usually, yes.
Yeah.
Leading to lower forces and potentially less structural damage.
Base slab averaging for large foundations, what does that feel like for the building?
For structures on large, stiff mat foundations, base slab averaging means the foundation filters out the highest frequency, sharpest jolts of the ground motion. The building rides the larger, smoother waves, not every tiny wiggle. This can be particularly beneficial for shorter, stiffer structures that are sensitive to high frequencies.
Smoother ride. And embedment effects bearing the foundation.
Embedding the foundation generally reduces the overall amplitude of the motion transmitted into the structure compared to a surface foundation. The surrounding soil helps constrain movement, particularly rocking, and can significantly reduce the seismic demands on the building.
So depth helps.
Generally, yes. These effects show that the ground isn't just passive support, it's actively participating in modifying the earthquake's input.
Okay, summing it up. When engineers properly account for SSI, what's the typical impact on the design forces calculated for the building?
Generally speaking, accounting for SSI tends to result in reduced calculated seismic forces compared to a rigid base analysis.
Reduced forces. Interesting.
Yes, especially for stiffer buildings or for the higher vibration modes of taller buildings. This reduction comes from the increased damping and the potential for beneficial period lengthening. BUT.
Another but.
Yes, and this is important from a practical design perspective. Building codes like ASCE 7 place limits on how much you can reduce design forces due to SSI.
Ah, they don't let you take full credit.
Often not full credit. It's a conservative measure to account for uncertainties in soil properties and modeling. So while the analysis might show larger reductions, you can't always take full credit for it in the final design forces required by code.
Building in some safety margin.
Exactly. You can't assume the ground will always make the building cheaper.
That makes perfect sense. So as we wrap up this deep dive, what's the single most important message you hope listeners take away about soil-structure interaction?
The fundamental takeaway is this. The ground beneath our feet is not a static, rigid block. It is an active, dynamic partner in how our buildings behave, especially when subjected to dynamic forces. Understanding and properly accounting for soil structure interaction is not just an academic exercise. It is absolutely essential for designing safe, resilient structures that can withstand the real forces of nature. Period.
And hopefully we've helped you unlock some surprising insights today. From the counterintuitive ways SSI can sometimes reduce forces, to the devastating resonance unleashed in places like Mexico City when the soil and building periods align, to just how complex and vital it is to understand that connection between the earth and our built world.
Absolutely. It really encourages us to think about structures not just as standalone objects, but as systems deeply connected to their environment.
So here's a final thought for you to consider. As our ability to model complex systems improves dramatically, as we get better at characterizing soil with more advanced tools, and as we incorporate nonlinearity, contact surfaces, maybe even real-time data from sensors, how might these advancements fundamentally change structural design? Could we engineer buildings that are even more intimately tuned, perhaps even adaptive, truly understanding and responding to their dynamic relationship with the ground through SSI?
That's a fantastic thought. I believe those technological and analytical advancements will undoubtedly lead to more refined, performance-based designs. It could open the door to structures that aren't just designed for static conditions with dynamic checks, but are truly engineered to interact optimally with the ground under dynamic loading. It could usher in a new era of safer, more efficient, and more resilient infrastructure, especially in seismic regions, but really with implications everywhere.
Fascinating possibilities. Well, this has been a deep dive into the world beneath our feet. Thank you for joining us. Until our next exploration, keep looking around and perhaps a little deeper at the world you inhabit.